2022, and this is the libembeddedhal meeting. All right, so some of the highlights for this week. We're gonna go. Sorry again. Oh, I think I'm hearing echo. So if someone could mute, or everyone can actually mute at this point while I go over the meeting, and then you can unmute when you need to. That'd be great. Yeah. So some of the highlights. Progress report, iteration 7. I'm gonna go over that and what we've done. Spoiler, not too much. Malia actually carried us a whole bunch, so thank you very much there. We'll go over web serial, which is live now, so that's awesome. A new project schedule, embed percent precision problem, and then also moving units to uint64, but all, I'm sorry, to int32, meant to say. And then also at the same time, deprioritizing all units and unit-based interfaces for now. I'll go into why that is. So yeah. So first off, let's just go into the project real quick. So yeah, Malia pretty much covered everything for the mocks. She got through 6 different mocks this week, so you know, for their work, thank you very much. And then on my side,
Hell of a job.
Yeah, good job. And then also fixed approximation errors for integer type division, which is where I'm talking about the whole us moving back to 32-bit. And I'll be explaining that in detail. So there's really not much else to say about this iteration. Next one's pretty packed. I think actually quite a few of these can get knocked out pretty quickly on my side. The ones that Sarah's assigned to can be knocked out pretty quickly, I believe. Davi's working on closest. Pretty much nearly done. There's one little design decision we're trying to make when it comes to the return type of this thing. This shouldn't be too hard for Sammy to finish up. And I believe Melissa should be available to work on this one this time. And then BitBang has been moved over. Okay, cool. So that's pretty much that. Let's now move over back to the slideshow. Let's get into the actual meeting. So web serial is live. Special thanks to Evan. He did a fantastic job on web serial, getting it up and running and just kind of setting it up. I'm actually going to show you what it looks like. The URL is libembeddedhal.github.io/webserial. Like libembeddedhal.github.io is going to pretty much be the URL for most things, then / whatever the name of the repo is. So let's click on this real quick. You'll be able to see what it looks like now. It's very different from telemetry. I got rid of some of the other text that was here, some of like the hyperload uploading stuff, cleared all that out. And we moved the version back down to 1.0. Put clear console and everything else like that on this bar so that it's out of the way, so you get the most amount of space for this as possible. And yeah, actually, so let me actually demo this. Let me get out my SJ2 board. Give me a sec. Should have had that ready, but didn't think about it until just now. That'd be cool to demo what that actually looks like. So, can I also change the fonts around? Tell me if you don't like them. I can always change them around. Not too sold on any particular font. Although I'd love to use just a web safe font. But that's what I did. And Dolly Mono is what I used. So, all right. So connected. You'll see. So the difference here is that the flow is like this. There's no longer a drop-down menu that tells you what things are currently available. Oh, also, let me actually roll back to the biggest part about this. You no longer need a Chrome extension, period. You also no longer are limited to just Chrome to do this. So that's the big reason why we did all this stuff, purely to get rid of the Chrome-specific requirement and to not have to build an extension for every single other browser that's out there. The web serial API is slated to be brought into the W3C standards for web browsers, and if that does happen, then we can see it being there for Firefox, Safari, and beyond, Edge, Opera, and Chrome and Chromium. I don't know if there's any other ones that are really that relevant. So that's pretty much what we will be able to get. So that's what we're looking for. Oh, and currently, because Chromium supports web serial API, everything else that uses it and derives from it also gets that as well. So that means Chrome, Edge, and Opera currently support this. So when you go to this page, which you'll see when you go to connect, where you pick your baud rate, go to connect, you see this little area over here pop up. You'll see different options. And what I want to do specifically is connect up to this. I wonder if, yep. So if I just unplugged it. If I plug it back in, come up. Yep, there we go. Connect. And a couple of glitchy stuff in the beginning. If I actually do DTR twice to just reset it. Yeah, it looks just fine. I noticed that it does do this in the beginning. It gets a couple frame errors before it actually kind of settles down. Not sure if that's something that I want to like fix per se, but we'll look into it. And yeah, that's pretty much it. Scroll up and down, normal typical stuff. I removed a lot of things from telemetry that don't make sense anymore. Like for options, really just dark theme, and that's about it. So yeah, that's pretty much it. This all works here. This doesn't actually do anything for this particular application, but you can still send data this way. You could upload a file, a text file particularly. You can also click on the center terminal and actually type in here as well. So you're not really limited to just using this bar up here to send data. Okay. Any questions, comments, concerns about it? Any suggestions? Cool. All right, disconnect from that. Actually, if you connect, one other cool thing, I've added this in. I think it might be better off that if we like add an area up here though. So if I remove this, it says existing serial monitored, exiting serial monitor due to error, network error, device has been lost. That's really great. I think if we have like a status up here so that we don't actually end up using up any of the real estate in the actual terminal, so it doesn't look like your actual device sent this. Okay, so that's that. Let's get back to it. So the new item here is the project schedule. So I think a couple weeks ago, I was thinking about like the whole alpha launch and how many things we had to support and handle. And I realized that didn't really make sense to just keep everything all together, like just one big launch with everything in there. I think it makes sense to split it up, specifically because I actually was thinking about the fact that we do so much for libembeddedhal on its own that as we add more interfaces or as we change interfaces, the any code below ends up breaking. So nonstop has all the other code been breaking. And that's when I realized that it might actually be better off to just go through all of libembeddedhal in a waterfall fashion, and then next work on the implementations. And at the same time as working on implementations, we then go back to say, hey, this implementation detail here actually results in this really weird behavior or puts us in a constraint that actually makes the code less efficient. We should go and change it back. So build up all the interfaces first. Once that's nice and solid to some degree, then we move over to implementing them. And then we do a feedback loop of, okay, does it seem like a good system? Does it seem okay? All right, well, that seems like a good API. That's fine. And we'll see little issues here and there. And then once we get past that point and we start building demos for our different libraries, next after that will be, and kind of ignore the units for now, will be project demo alpha stage. So after we've done the implementation wave, which incorporates all of like the STM libraries and LPC libraries and that kind of thing, then we'll work on the projects. And with the projects, we'll be able to also kind of iterate on whether or not we're making the right choices when it comes to serial, when it comes to I2C, when it comes to GPIO input and outputs and that kind of thing. And we'll continue to ask questions to ourselves, like, is this the right choice? And maybe we ask other peers of ours or look at our own things that we're doing around in our own projects, our own companies. Say, hey, you know, the way that we're doing GPIO actually makes sense because we need this thing, or we shouldn't have this thing here because it's too low level or whatever, or not everything supports this. So really it's going to be a feedback loop back to libembeddedhal, but I think it makes sense to have libembeddedhal be launched sooner than later and have it actually be on Conan so that we can actually use it for other libraries. So September 6th, which is our early launch date, is what we had slated for it. I'm moving that to becoming the actual launch date for libembeddedhal. No longer the early one, just the launch date. But we don't have too many libraries or too many hard libraries to build to get there. So I feel pretty confident that we can get there. Implementation wave is going to take a while, probably around about October 8th, maybe even further than that. But I'll explain how we're going to prioritize some of the items in the next couple bullet points. Unit-based interfaces. So this whole talk today is actually going to be really talking about some of the problems we had when it came to units. And specifically, it's also going to talk about how I decided to break it off into its own project, because it did turn into its own. As I was talking to another friend of mine, they said that the work that I was doing seemed akin to trying to solve MATLAB simulation precision problems, but in a really confined space, embedded. And, trying to solve this problem just seems like this feedback loop of having to do it over and over and over again, like we have been doing over and over and over again. And what it's really just going to do is we're gonna end up making a mistake. My fear is that we're going to say, well, this is good enough for now, and then actually start developing things and realize it's a complete mess, and then not know what to do from there. So I kind of want to create a separate group to just work on how we handle units in general going forward, and I'll have some explanations as to why the things that we had thought of before didn't really work out. And then finally, the project demos. So one of the big ones is going to be supporting the robotics team at SJSU, as well as also possibly making an MP3 project. I'm a little bit not sure about that because that is a project for classes at San Jose State, but it's a thing. But yeah, robotics team is going to be one of the biggest customers, and they will help to really fish out all of the weird aspects of the API, things that don't make sense, things that are difficult to do, that kind of thing. So that's going to be fantastic. If you guys have any other ideas beyond the MP3 project and the robotics team that we could contribute to or work on as projects, please send them my way or put them on the discussions board for Discord so that we know we have an idea of like, so we can kind of collect them and see which ones make the most sense. I already explained the next bullet point, so I'm gonna skip over that. The implementation wave alpha stage. So just there might be implementation beta. So if you see the alpha stuff a lot, it's just because I'm gonna use alpha beta. We might iterate over this a couple times before we settle on the final launch candidate that will actually push out there and then try to advertise. We're going to prioritize components for robotics first because they will actually need our stuff sooner than later. They can move over to our stuff as soon as possible, where the MP3 project and other things like that can take time. The MP3 project is helpful, though, so I can actually see the difference between writing the MP3 project with SJC Dev 2 as well versus writing it with libembeddedhal. And if anyone could make a version of that with parity of features on Arduino and other systems, that'd be great, although that's a big ask. I'm not asking anyone in particular to do that yet, just something that considered so that we can have a comparison. Any questions about the new project schedule? Oh, and yeah, the dates for unit-based interfaces and projects, no clue at the moment, especially if you start adding more projects. So that's still kind of in the works, but we will probably come up with some due date when we feel like it's becoming more pressing to have these things developed. Oh, and actually one thing to note is that just because we don't have interfaces for unit-based interfaces, we don't have an interface for interfaces that require units, like for example, accelerometer or gyroscope. Accelerometer being acceleration, gyroscope being rotational velocity or angular velocity, does not mean that you still can't build libraries that implement that are actually accelerometers. They just won't be able to be passed to other objects that expect a certain defined API. So that's that. All right, now I kind of made this entire screen green just to kind of say we're going to focus in on this percent precision problem. So percent precision problem. This is number 2 here. Oh my goodness, how'd this happen? Okay, it's supposed to be, did these get out of order? The number title is just out of order, so that's my bad. I'm surprised I missed that. Anyway, so this little red bar, it should be about a quarter. It doesn't look like a quarter though, and this is my eyes, but this red bar kind of represents the percentage. The green portion represents 1/4 of that percentage. So 1/4 of it, or 25%, or that number, what is that 536,870,912 out of 2 to the 31 minus 1, which is basically the maximum number you can have for positive numbers. So that is how we represent our percentages. We have some number that is that percentage of a value from the domain of 0 to, or from negative maximum for 32 bits to maximum for 32 bits. And that's how we represent percentages, and it works out pretty well because you get a good amount of precision with this. This percentage gives you around 9 decimal points, which is about 3 digits more than 32-bit floats. 32-bit floats only get you around 6 digits. Technically 7-ish, close to 7, but no, you only really get 7 full solid digits. So we get a lot of precision and quite a bit of accuracy and also performance compared to using floating point numbers. And we can use this to basically scale up and down other numbers by basically multiplying this number by some other number, scales up to a 64-bit number, and then we can divide it back down to bring it back to what it really should be. That math there, you can look at the percent class to get more details. I think I may actually explain it the next one, though. Yeah. So in this process, working on linear, so here's where the problem comes in. So the previous is just a recap of how it works, but in this process, we were, in this time, what happened in this last couple weeks is that we were working on linear potentiometer, which implements linear encoder, and we realized that since our linear, our units were in 64-bit, we would need, when we did the scaling, we'd need a number that's bigger than 64 bits. If you multiply any two numbers together, whatever the number of bits are, the end resultant to hold them needs to be the addition of the 2-bit widths. So for example, if you have two 32-bit numbers and you multiply them together, you're going to need a 64-bit container to hold it without there ever being an overflow. There's no two 32-bit numbers that cannot fit inside of a 64-bit number. So in order to make sure we don't have to worry about overflows, or to make sure we can actually scale them up without overflows occurring, we needed an int 128. Oh, I guess one thing to say is not just be concerned about overflows, but also to ensure that the end value, like that we don't have errors coming out of nowhere just because our math can't handle it. Our math should be able to handle this, scaling up and down a 64-bit number, at least back when we were working on this. So int 128 was required. Now, that's not always supported on all platforms, so we brought in a library called uwideint, uwideint, unsigned wide int. And what we do is just multiply the two 64-bit numbers together, put them inside the 128-bit number. The source of these numbers, these 64-bit wide numbers, came from all of our integer containers, which were basically just our units. When we had our units, we always used int64 because that allowed us to have such a large range of values that it did not matter what you really chose. You probably would never reach the numbers we would worry about. For example, the maximum temperature you could have from 0 Kelvin up to 2 to the 63 power is, I forget how much hotter than the core of the sun, something like that. So it's either the core of the sun is much bigger than the surface of the sun, that's for sure. So that was the thing. But one of the issues that we had was that, due to the percent using int32, the results of the math were imprecise, resulting in incorrect answers. The only real way to solve that problem, and I'll get into why that's a problem in a sec, was to basically bump embed percent to using 64-bit numbers. And now what that then requires is that every single operation that happens on a percent object will now require int 128 in order for it to work by default. At first I thought that was not the biggest deal. That's a bit of a cost, seems a bit much, but hey, if it's simple for the compiler to handle, I don't see why we couldn't just do that. And this is where I'm going to start explaining how this kind of breaks down. So if we take and analyze the 500 million value divided by the maximum for a 32-bit number, positive or signed, I meant to say, you'll find that the ratio ends up being like this: 1.25, which is correct. It's a quarter. Then 0.0000, and then you have all this other noise back here. Now let's break this down into just the zeros. Boom. That's exactly what we need. If we just kind of round off at this point here, we get exactly what we need. Now notice that this is the exact number of precision that we can support for. There's about 9 digits here. That 9 digits isn't a mistake, isn't a coincidence. We have nine digits of precision here because when we actually do our multiplication against our whatever values we're working with, we know that the end result, when we do all the rest of the operations, will get you back down to a value that basically ignores all this other stuff. All this other stuff basically gets eliminated. All that process noise here gets completely destroyed. So now when we attempt to perform the same type of math on int64-bit numbers, we get problems because 64-bit numbers can have up to 18 decimal digits of precision. So with our 9 decimal points of precision, we run into this issue here. So let's say we have 25% of this large number, it starts with a 4. It should be this large number that starts with a 1, but we get this. If you run this through Wolfram Alpha, which is what this particular link brings you to, take this number times this number we're using before, divided by this, you end up getting 1, 0, 0, 0, 0, 0, and then you get this bit of noise in here. You get this extra process error. You get this lack of precision. And this is not correct. This is not the right answer. The right answer is right below. We did the same exact thing here. This number here is 25% of 2 to the 63. Do all this math together, you round it, and you get this number. That's exactly what we're looking for. So this may indicate that, moving to int64 was the right choice for percent. But here's where we hit the real problems. Here's where you'll see the issues here. So when we moved over to this, I needed to know if this was any better than using floats. And we found out that actually for multiply and divide, we ended up costing us 3,328 bytes. Whereas 32-bit and 64-bit floating point arithmetic and all operations, multiply, divide, plus, minus, comparisons, all that kind of stuff, 3,200. And at that point, I was thinking about running a performance test, but I also felt that it didn't make the most sense to kind of just look back before we even go to performance tests. Just kind of look at whether or not this would make sense just from a numeric sense. And when I looked at the actual code gen for it, it wasn't as small as I was hoping it would be. Even when I rolled my own implementation for this, the code gen was actually a lot more extensive than I was kind of hoping for. So if we look at int64, you get 18 bits of precision, which is fantastic. You get no precision loss, totally fine. The performance is slow, and the cost in Flash is 3,300. So performance has not been tested, but code side does look complex, so it's probably as complex. There's a bunch of iterations and loops in there to do a lot of work. I believe it's also dependent on the number, because it's doing long division for your values. So there's a good chance that the bigger your number is, the slower it'll be. So that means that the operations are a little bit less deterministic, or not as deterministic. Float, 6 digits, very poor. Precision loss, yes. Slow, but faster than FPU. So if you have an FPU, this is actually not it's a couple more cycles than you get from normal integer math, but it ain't too bad. Double, 15, it is slow and costs quite a bit. And yeah, my little note here, just in general, math may not work if values are too large or too small. That's actually one of my biggest concerns, is that if you have a very large value for your length, and you add 1 to it, like 1 more meter to it, and it's like, let's say 1 quadrillion meters, whatever, and 1 more to it, that 1 will go away. It will fall off. You'll have a precision loss at that point. The value will not be added in. So you can add that thing an infinite number of times. It'll never you'll never see that value actually increment. So that's one of my concerns with using floating point arithmetic. And the alternative would be to use them, and you have to document all of your code really thoroughly to make sure that precision loss never happens. We still have to do that kind of, but not as much. And then we have int32, 9 digits of precision for decimal numbers. No precision loss. It's very fast, and the cost of the udev mod i4 function is only 720 bytes, so it's pretty minimal. So that's kind of what we're looking for. But the biggest note about this is that it requires all the units to be 32-bit for it to be unlikely for us to ever need to use 128-bit. And that's when I thought to myself, that's a pretty hefty ask. But let's look into it anyway. So I kind of looked at this one because this one fit our performance situation. Now let's think about it. Why move all units to int32 type? Fast and cost very little storage. The actual integers itself are half the size of 64 bits, so that's great. It's fast to do operations on. We're kind of targeting 32-bit systems, but I understand that we're going to be on 8-bit and 16-bit systems as well. And having 8 bytes representing a number is quite large, and I was willing to accept that so long as using 128 wasn't any worse. But once I saw the numbers there, it can only get worse once you go down to smaller architectures. So fast and fast and very little storage. I personally have confidence that most applications only really need 32 bits of range for units, but I could be very wrong, and I'm more than happy to when we make that group for units for us to really discuss it, because I am not sure how to proceed going forward. Udiv mod I, basically just doing division for that. Usually likely to be used. It's very likely to be used in most applications. So having it as a dependency is not that big a deal. It's automatically generated by the compiler. Most compilers have to support up to int64 for any C++ or C conforming compiler. So yeah, that's the thing. Interfaces with higher precision could be introduced for systems that require it. So for example, let's say you do need like a 64-bit nanoscale system. Well, in this case, what we kind of have is pay for what you use. If you use the basic low precision or normal accelerometer, then you don't have to pay for all the additional math that comes in from doing the high precision stuff. But when you need high precision, specifically you need high precision, then you can then use that interface. And now we can have interfaces that say, hey, I can use any accelerometer, or some of them say like, no, I need specifically a high resolution accelerometer. If I don't have that, then my systems will not work appropriately. So now libraries can have that choice. And then like for certain types of units that need larger numbers, there's a kind of a clever method for, extending your range, but only on the positive side. You can't, in this case, with the sample over time approach, get higher precision. You can only just get bigger ranges. So, moving from int64 to 32. So I kind of have this chart. I have this chart here that goes over the min-max ranges for int32 types. Kind of going over a whole bunch of different ones, and the green highlights which one we've selected. Again, this is all very tentative. We may have other discussions that go into the details here that indicate to us that we're making the wrong choice and we should change it up. But I want to go over a couple of these. So let's go over time. Time's one of the most important ones here because if anything, the one units people are going to use a lot and the one that we're going to have to continue to support regardless of how we choose units in the end, time is one of the big ones. If we were to use nanoscale for time, so nanoseconds for time, we'd only be able to discern two seconds, basically. The maximum number for a 32-bit number can only reach up to, for nanoscale values, up to 2 seconds. For micro, we can get up to 35 minutes. That's pretty short, but there's actually ways to get around this. Time is actually one of those ones where if we kept it at 32 bits, we'd be pretty fine in a lot of use cases. Millis gives you 2 million seconds, which could be a very long time. I believe it's in the order of years. So that's great. And then if you just do base 0, then you get large numbers, but obviously doing everything by a single second isn't really helpful. So I'm thinking that 35 minutes works out, and particularly for time, we can discuss that a little bit later in the next slide. Frequency, what we currently have is basically baseline, so you really can't get anything smaller than a hertz. And if you really needed that, you should really just be using time to represent whatever you're doing. So we just kind of go full sail, positive only, no negative frequencies, and go 4.294. That's the biggest frequency that we can support. I am considering making it plus or minus, making it signed, so that the arithmetic can be a little more safe, but we'll see. Length. This is where I thought, 2.1 kilometers for most situations probably fits most things. I mean, linear encoder may be able to track beyond that, but I think as long as it's going in one direction and you can kind of check the difference between every measurement you do, there's a way you can kind of solve that problem. So length works out pretty well if you have a linear encoder that can kind of go on forever. That's relative. Angle, the idea now is to actually use rotations versus using radians. MP units uses radians. There's currently a big discussion right now on the MP units on what we should be using. I've been pushing I've been suggesting to the team that we should stick with rotations. Specifically, we should eliminate the concern when it comes to transcendental numbers, specifically with pi. I think if we just set pi equal to 1 or set pi equal to, or set one rotation equal to 2 pi, then we can have mathematics that has no precision loss, then whenever you want to convert it back into real radians, you can actually multiply it by pi, provided whatever type you're using. So if you're using a float, it'll be 3.14 whatever else is until you hit 6 digits, and that's when it all ends. And that's as much precision you'd be afforded with that type anyway. So that's the thing. If you just use rotations, you can get macro rotations, so 1/1000th of a rotation, which I think is a pretty good fine resolution, and you can get up to 2,000 rotations in total. So I think that's a pretty good way to work this out. For acceleration, 2000 G. I did find things that could possibly do higher than that, like 10,000 G, but most of the things I saw on Mauser and DigiKey could only really pretty much topped out at 2G, at 2000 G. So we don't really need to go beyond that. Oh, and this will be in units of G, no longer meters per second or nanometers per second squared. Because I think just using G makes more sense for most accelerometers because they're almost always in that range or use that particular unit. And then Kelvin. I think 2000 Celsius is a pretty large number, but I could be, or 1800 Celsius. So I could also be told otherwise. I'm going to try to not spend too much time on this one. But basically the approach here, so we have this thing called uptime counter. And we know that when it comes to uptime, it only goes up to 32 bits. And there are a lot of counters that they run fast enough can really overflow their 32-bit unsigned counter. So how do we calculate bigger numbers without slowing down the counter? If we want high resolution, but we want long range, how do we emulate this when we only have a 32-bit counter? Well, what you can actually do is you can actually sample over time. So if you sample, well, remember, our overflow time is about 35 minutes. You may want to sample twice as fast. I think this might be required, but basically, yeah, twice as fast. You want to sample every 15 minutes. It could be a good ratio. That way, you can detect overflows. And when you detect these overflows, you can basically create the delta between what your previous value was and your new value is, and just sum them. And actually, there's a fun little capability of unsigned numbers where no matter if you subtract if you know that one number, the first number is supposed to be bigger than the second number, and you always subtract them, you'll always get the distance between them, even if they overflow. So if you have, like, let's say 15 minus 2 billion, you will get the distance between those numbers. It wraps around. When you subtract them, you actually get the value that wraps around, and that's actually part of the C and C++ standard. So that works out. So you can actually basically sample over time and keeping time up until however long you want to keep time for, whatever your size container is. But it does not work for things like accelerometers or like temperature sensors because those are absolute values. You can't accumulate acceleration in order to figure out that you had a bigger acceleration later on. That doesn't really work. So that's this approach. So it works for some, like length if you have a relative encoder, or time. That works for those ones. Angle too, because if you keep rotating, and you overflow, you can continue to look at the difference between those. But acceleration and temperature do not fit this, and very many other ones won't fit this either. Let's say you think about timeouts. Maybe you're thinking in your head like, well, does that mean that if we create a timeout using an int32, we can only wait about 35 minutes? What if I want to wait an hour? Well, this is actually pretty simple. You can have a timeout that supports 64-bit timeouts, or 64 bits of time. And simply put, you can just wait time slices of 35 minutes. So you have a timeout that basically runs for 35 minutes. And when that one expires, you then run another one, and another one, and another one. And you keep doing that up until the point where you finally reach your end result. You just have to have a counter of some sort to know how many of these maxed out timeouts you've basically iterated over. And then whatever's left over, you just throw that in as the next timeout. So that's how you handle that. All right, so I know I've gone over a lot. Any questions so far about what we've gone over? Okay. All right, so looking at the UI int dependency. So we brought in the library specifically to support int 128. And if we eliminate the needing to do scaling beyond int64, this library really isn't needed. And if we bring the space, or the container for almost all of our time durations down to int32, and and we only really need nanoseconds or like just a in 64 microscale. Sorry, time scale, a time duration using 32-bit numbers and having it at micro for the scaling. We actually shouldn't ever really need in 128. We may need it in the future, but at the moment it can be eliminated. And to kind of help enforce that, I've gone and actually deleted that library because we weren't really using it that many places except for when we needed it with frequency or when we need it for percent. So for now, that's not available. And hopefully, if we do need it, we'll bring it back in. But this all kind of, thinking about this and what units to use, and this created even more problems. Because now I was thinking about like, well, what about the MP units class, library? How much is that taking up from us? And it turned into a deep dive. It's not illustrated here, but it turned into a pretty massive dive into, how do we handle units in general? And maybe we shouldn't even be handling units directly like MP units does. Maybe we should say, you know what, we just use an int that represents microgravity or like microgravities, divisions of those. And if you want to use those type of units libraries, you can pass them into these units libraries and do those operations yourself. Basically, leave that up to the user to implement that part, and also the drivers too. Let the driver choose what they want as well. So long as the units library doesn't stick around, meaning that like it boils away into just doing normal math, then using whatever units library you like for doing your operations should be fine, so long as the end result fits our standard for what the units must be. So that's pretty much the main cap here. But the points I put in here were MP units is very incomplete. They're missing things like G, rotations, Celsius. Celsius was one of probably the biggest parts that was kind of annoying to deal with. I totally understand why it's complicated. Just also the fact they don't have it yet is something that we have to kind of wait on. It's also very complex. It's very complex to kind of use. It's not the easiest to kind of get used to. Like I said here, it's not clear if we should actually define a standard for a unit library, or if we should, go very basic. And because of all these different things that came up after considering what the unit should be like, I think it makes sense that we make it into its own project. We deprioritize it for now so we can focus on the main primitives for embedded and go from there. And that then means that these are the type of interfaces that are going to be deprioritized. The compass, the accelerometer, the gyroscope, temperature, linear encoder, rotary encoder, and light sensor. So I apologize for anyone who has worked on these ones recently. If you do have a passion for trying to figure out this particular problem and you would like to consider and think about like how to solve this problem going forward, I'd be more than happy to work with you so that we can like continue on this. But if you want to work on other things that are more important to the launch, these will no longer be of concern. So the code's going to still be around. I have gone in and basically gutted MP units and other things like that out of the project, just to get the code size of the project down to what's reasonable, as well as also just to kind of make it clear that like these libraries aren't really complete. But if you want to work with me on that, that'd be fantastic. And that is pretty much it. Any questions about deprioritizing unit-based interfaces? Alrighty, I'm going to thank you guys for coming along.